Welcome everyone, and thank you for joining us for today's webinar, Automated High-Efficiency Solid-Phase Peptide Synthesis of Modified and Pharmaceutically Relevant Peptides. My name is Gabrielle Thalhammer, and I'm the Life Science Marketing Specialist for CEM Corporation. Just a little bit of housekeeping before we begin. If you have questions during the presentation, please type them into your GoToWebinar control panel. We'll have time to answer all your questions at the end of the presentation. This webinar will be recorded and will be available to view on CEM Corporation's website following the webinar. Now, I'd like to turn the mic over to our presenter, Alexandria Brackbill, the CEM Life Science Applications Chemist. Alexandria?
Hi everyone. Thank you for joining me in this webinar on the automated high-efficiency solid-phase peptide synthesis of modified and pharmaceutically relevant peptides. In today's webinar, we are going to cover the variety of synthetic applications possible with the Liberty Blue automated microwave synthesizer. We will cover the methods of peptide cyclization, peptidomimetic synthesis, and peptide modifications displayed in this outline. Please note that the topics in light gray will not be discussed for brevity's sake. However, if you would like more information on these or any other topics covered today, you can visit our website or email us at peptide.support@cem.com. Before we get started, I wanted to provide you with some more information on the instrumentation and reagents utilized. All peptides are synthesized fully automated on the Liberty Blue peptide synthesizer. Peptides were cleaved at 41 degrees Celsius on the Razor cleavage system. All UPLC mass spec analysis was performed on a Waters Aquity UPLC with PDA with a Waters 3100 single quad mass spec, and all peaks were analyzed using the MassLink software. Oximapure, all resins, and nearly all amino acids, both standard and non-standard, were supplied by CEM Corporation. DIC and a handful of non-standard reagents were purchased from EMD Millipore, Peptides International, and Sigma Aldrich. All other standard laboratory solvents and reagents used were purchased from various large chemical suppliers. Lastly, while the Liberty Blue can synthesize peptides from the 5 micromole to the 5 millimole scale, all peptides presented in this webinar were synthesized at the 0.05 or 0.10 millimole scale, unless otherwise stated. Now let's begin by looking at the methods of peptide cyclization possible on the Liberty Blue. First, let's look at RCM and hydrocarbon stapling. You can see here that stapling is a form of cyclization which joins the side chains of 2 amino acid building blocks. Stapling is known to stabilize alpha helices and has been shown to increase protease resistance and increase cell permeability. Perhaps the most common method of stapling is hydrocarbon stapling. Let's take a look at this peptide, BID-SOB. You can see that this peptide is cyclized via this alkyl chain with an internal alkene. We can access this peptide by first incorporating 2 building blocks with terminal alkenyl R groups, such as this 4-pentenyl alanine derivative, which is denoted S5, and then subjecting it to RCM with Grubb's first-generation catalyst. By automating this synthetic approach, we were able to access BID-SOB in 80% crude purity in less than 4 hours. Incorporation of the alkynyl residues was simple, and to staple, the peptide was heated to 40 degrees Celsius with Grubb's catalyst for a total of 1 hour. Next, let's take a look at disulfide bridging, which is the oxidative bond formation of 2 thiol-containing R groups, namely cysteine. Disulfide bridging is found in many biologically active peptides, most commonly venoms and therapeutics. The disulfide bond stabilizes secondary structure and, like stapling, can increase protease resistance and target affinity. But how can we form these synthetically? Let's look at oxytocin. Working backwards, we know that we need to incorporate 2 cysteine residues. However, the protecting group utilized on the cis building block is important and should be able to be deprotected while leaving the rest of the peptide protecting groups unharmed. A commonly used derivative is cis-MMT, which can be deprotected with dilute TFA to furnish the free thiols. Upon furnishing these free thiols, the peptide is subjected to NCS for disulfide formation. By applying these principles and automating the synthetic approach, we were able to access oxytocin in 69% crude purity in less than 3 hours. Incorporation of cis-MMT was simple. To deprotect MMT, the resin was treated with dilute TFA for a total of 10 minutes. Lastly, to form the disulfide bond, the peptide was subject to a solution of NCS for 15 minutes at room temperature. However, numerous peptides have multiple disulfide bonds, such as this conotoxin peptide. How do we form the correct bonds between thiols? The answer is simple. Working backwards, you know that you can use cis-MMT in the formation of one of the disulfide bonds. However, now you need a second orthogonally protected cis residue. Another common derivative is cis-STMP, which is deprotected with dithiothreatol and N-methylmorpholine. Using this approach, we were able to access conotoxin SI in 67% crude purity in under 4 hours. Like incorporation of cis-MMT, incorporation of cis-STMP is simple. Upon synthesis of the linear chain, the cis-STMP residues were deprotected by treatment with a solution of DTT and NMM for a total of 15 minutes at room temperature. Treatment with NCS furnished the first disulfide bond. Then, the peptide underwent cis-MMT deprotection and oxidation of the second disulfide bridge to furnish the desired peptide. In addition to hydrocarbon stapling and disulfide bridging, other forms of peptide cyclization able to be performed on the Liberty Blue include head-to-tail cyclization and side-chain-to-side chain condensation. However, for brevity's sake, let's move on to peptidomimetic synthesis, and particularly peptoid and peptide hybrid synthesis. Peptoids are polymers of various N-substituted glycines. They are resistant to proteolytic degradation, which is attributed to the complete substitution of their amide bonds. This makes them an attractive target for pharmaceutical development. Additionally, the secondary structure of peptoids are altered due to their lack of amide hydrogen. Incorporation of a peptoid monomer is not as simple as chain propagation with FMOC N-substituted glycine derivatives. Instead, a two-step acetylation, then nucleophilic displacement approach is necessary. First, bromoacetic acid is coupled traditionally to the N-terminus of a peptide or peptoid monomer. Then, addition of a primary amine displaces the bromide ion, furnishing the N-substituted glycine residue. At this point, the peptoid is ready for further chain elongation with no FMOC removal necessary. This two-step procedure, though not as simple as one-step incorporation processes, offers great flexibility. There are thousands of commercially available amines that can be employed in peptoid synthesis, opening up much opportunity for chemical discovery. Using this approach, we were able to synthesize the peptoid-peptide hybrid displayed here in 81% crude purity in just under 2 hours. For peptide monomer incorporation, the resin was first treated with bromoacetic acid and DIC for 5 minutes at 75 degrees Celsius. Then, the resin was treated with the necessary primary amine for 5 minutes at 75 degrees Celsius also. To note, incorporation of amino acids upon peptoid monomer installation was quick and simple, using 4-minute 90 degrees Celsius coupling times. In addition to peptoid synthesis, PNA monomer incorporation is another peptidomimetic application possible with the Liberty Blue. Though omitted from this webinar, please feel free to email peptide.support@cem.com for more information. In the meantime, however, let's take a look at this webinar's final part, peptide modifications. First up, which may be obvious from peptides displayed earlier in this presentation, is N-terminal acetylation, which is a widespread modification among eukaryotes and prokaryotes alike. N-terminal acetylation alters the charge and hydrophobicity of the peptide, affecting its folding properties and target affinity. Additionally, protease resistance can also be increased by N-terminal acetylation. Automated N-terminal acetylation is simple. Upon FMOC deprotection of the N-terminus, the free amine is subjected to 10% acetic anhydride at 65 degrees Celsius for just 2 minutes. This modification is quick and simple. Next, we are going to look at the incorporation of non-standard, hindered amino acids, such as quaternary center-containing AIB or nitrogen-substituted N-methylalanine. Incorporation of these types of derivatives is becoming increasingly popular. AIB induces alpha helix formation, and N-methylalanine, like peptide monomers, increases protease resistance and alters secondary structure. When looking at incorporation of these building blocks, all is simple. Adding one of these hindered amino acids uses our standard single coupling of 90 degrees Celsius for 2 minutes. If you will be attaching a hindered amino acid to another hindered amino acid, an extended double coupling is necessary, though this still only requires 5 minutes at 90 degrees Celsius. Lastly, attachment of a natural amino acid onto a more hindered residue requires a standard double coupling. With these methods, we were able to synthesize 2 ACP variants with these hindered building blocks in the place of alanine. In the AIB test, the desired peptide was furnished in 95% crude purity and in under 2 hours. Similarly, the desired peptide in the N-methylalanine run was synthesized in 86% crude purity within 2 hours. Next, we are going to take a look at the incorporation of phosphoamino acids. Phosphorylation introduces a phosphate group onto tyrosine, threonine, or serine residues of a peptide. Enzymatic phosphorylation regulates the function of many peptides and proteins, and synthesis of phosphorylated peptides can assist in the study of their functions and signal transductions. Traditionally, production of phosphorylated peptides required synthesis of the unmodified linear sequence, followed by a post-synthetic phosphorylation step. This step is difficult to perform and often yields impure peptides. The introduction of FMOC-derived monobenzyl-protected phosphoamino acids, such as those depicted here, has significantly improved the synthetic process. All 3 of these derivatives can be incorporated with ease on the Liberty Blue and use our standard coupling procedures. Phosphoserine, however, requires room temperature deprotection as it seems prone to dephosphorylation at high temperatures during deprotection. Upon incorporation of its neighboring amino acids, elevated deprotection temperatures can return for use. Lastly, when incorporating amino acids, we recommend addition of 0.4 molar DIEA to the oxima solution. This further prevents undesired dephosphorylation. With these parameters in mind, we were able to synthesize the displayed phosphopeptide in 82% crude purity in just under 2 hours. Let's move on now and look at symmetrical peptide branching. Symmetrically branched peptides often have highly desirable physiochemical and biological properties, mainly due to their multivalent binding ability and improved protease resistance. As we see here, this peptide has 4 separate chains of identical amino acid sequence. But how do we get to this point? First, we must look back to the first occurrence of branching. Here, we see that it is traced to this first rightmost lysine residue, which then branches to 2 more branched lysine residues. The residue responsible for this branching is actually FMOC lys-FMOC. With this in mind, we can see how treatment with deprotection solution would furnish 2 free amines ready for chain elongation. Looking back on our model peptide on the left, we see that the original lys-FMOC derivative was actually coupled to 2 more lys-FMOC derivatives, which in turn opened up 4 sites for simultaneous chain elongation. Using this approach, we synthesized this tetrabranched ACP peptide. The peptide was furnished in 70% crude purity and in under 2 hours. No specialized cycles or methods were required for this impressive molecule, and all standard single coupling methods were employed. Of note, because 25 micromole of resin was used, 100 micromole scale settings were employed to ensure adequate reagent delivery. However, you don't have to stop at tetramer branching. You can take it a step further, as we did with this G3KL octamer, which also includes lysine and leucine residues throughout the branching framework, not solely at the termini. This octamer was synthesized in 80% crude purity and in under 2 hours. Again, all standard single couplings were employed. To accommodate the increased terminal elongation points, 25 micromole of resin was used with 100 micromole synthesis scales, and reagent delivery amounts for the 100 micromole scale were doubled. These crude results are particularly astounding because the synthesis of branch peptides via SPPS is often challenging due to the inherent close proximity of elongating peptide chains. Application of microwave energy helps overcome the challenges of steric clash and poor coupling efficiency, as demonstrated here. We are going to move on now and discuss the automated orthogonal lysine deprotection and functionalization. Peptidyl side chain functionalizations such as bioconjugation, tagging, and branching are impactful and essential synthetic tools. While many amino acids can be functionalized, lysine has received particular attention. Similar to disulfide bond formation requiring orthogonally protected cis residues, lysine functionalization also requires protecting groups that can be removed without affecting the remainder of the peptide. Perhaps the three most common derivatives include lys-MMT, lys-IVDDE, and lys-ALOC. While MMT undergoes deprotection under weakly acidic conditions, lys-ALOC requires a palladium catalyst, and IVDDE requires dilute hydrazine. To test and develop automated methods of orthogonal deprotection for these three derivatives, we looked to couple alanine to the lysine side chain of the HIV-1 antibody epitope GP41, residues 659 to 671. The target peptide was successfully accessed through MMT removal, and coupling of the side chain with alanine, the peptide was furnished in 79% crude purity in about 3 hours, with MMT deprotection occurring for a total of 10 minutes at room temperature. Similarly, the target peptide was accessed through ALOC removal, with the peptide furnished in 82% crude purity in around 3 hours. ALOC removal required a total of 10 minutes at 35 degrees Celsius. Lastly, an acetylated version of the aforementioned peptide was successfully accessed through IVDDE removal. Acetylation was performed in this case as hydrazine deprotects FMOC groups as well. Alternatively, BOC rather than FMOC protected amino acids could have been employed. This peptide was furnished in 93% purity in around 3 hours, requiring a total of 9 minutes at 90 degrees Celsius for deprotection of the IVDDE group. Let's look at asymmetrical peptide branching as an extension of lysine functionalization. We can see here that this LF chimera peptide has two distinct points of chain elongation, one which is the original peptide chain, and the second an extension of its lysine side chain. With this knowledge, we know that we will need to first synthesize the linear chain, then deprotect lysine, and further elongate. Lys-IVDDE tends to be the orthogonal derivative of choice, so if we don't want to acetylate, we will need to use this BOC-protected phenylalanine building block in the last position of the original chain. Upon capping with this BOC-protected amino acid, we are free to deprotect lys-IVDDE and build the sequence that elongates from this point. Using this exact approach, we were able to furnish this LF chimera peptide in 77% crude purity in under 5 hours. All amino acids were coupled via our standard single coupling cycles, and IVDDE removal was performed as mentioned previously. Similarly to symmetrically branched peptide synthesis, we can take asymmetrical branching a step further, as we did in the synthesis of this tetrabranched antifreeze peptide, which was synthesized in 71% crude purity and in under 5 hours. In this case, the original peptide was synthesized incorporating lys-IVDDE at the desired points of branching. Upon N-terminal acetylation, IVDDE removal was performed, and the resulting free amines were coupled. It is worth noting that in this case too, 25 micromole of resin was used, but with 100 micromole scale settings to accommodate the increased coupling positions. And this wraps up Part 3, Peptide Modifications. Other peptide modifications compatible with the Liberty Blue, though not discussed here, include incorporation of glycoamino acids and orthogonal glutamic acid deprotection and functionalization. For more information on these topics or any other topics discussed today, please visit our website at cem.com or email us at peptide.support@cem.com. With that being said, I'd like to thank you for your time and answer any questions you may have. Thanks.